what data science based companies do is that they try to analyze the data and help companies to make decisions about how to optimally run their business, or in what way the business should progress so that it can be more efficient and so forth. That's what mainly the data science focuses on. And data science is sort of a broader domain. It of course involves machine learning techniques within data science so that it can make these sort of useful decisions. So machine learning of course plays an integral role, or we can say that it plays a dominant role within data science. So it is a part and parcel of data science. So that's what machine learning is used as a tool there. So now when we talk in terms of business intelligence here, so the business intelligence and data science, they are not essentially two entirely different things. So they are very much correlated. Where we can say business intelligence is nothing but it is a sort of a methodology by which it supports making better decisions for the business. So we make use of whatever available tools to come up with these conclusions to make better decisions. And when we think along that line about taking decisions for a company, one particular domain takes a very integral part in that, and that part is called data mining. So that plays a crucial role in making these decisions. And we can ask the question, so what is data mining now? So data mining is, briefly we can think of it like it's a process of discovering or deriving some useful information from data. So that's what essentially data mining is. Mostly we discuss that in the context of big data analytics. But big data or not, the techniques that we use there essentially is used to derive some useful information based on which we make some decisions. So that's what essentially what data mining captures. And data mining involves machine learning tools. It involves predominantly statistical techniques. And as we are talking about, it is trying to derive useful information from data. It could be small or large big data analytics. So we need a well-defined system to store data set. So it will also include database systems. So we can essentially capture data mining as sort of an intersection of machine learning, statistics, and database systems. So that's what essentially data mining methods are. So why we needed to come up with such data mining technique essentially is that, so nowadays we are essentially dealing with humongous amount of data. Like we can say, for example, Google uses billions of data for its analytics. So surplus amount of data are available in internet now. And the number of features, so high dimensionality means the number of features that we usually deal with while processing the data is also extremely large. Especially when we take natural language processing, for example, when we talk about text analytics. So text analytics is also an integral part of data mining, essentially natural language processing. So when we do that, you can see that the number of features that we deal in text analytics is exponentially large. So we are dealing with very huge dimensional data when we are doing text mining. So we need efficient techniques to handle that. And the data generally, so I'm just highlighted about text data, but data can be even otherwise complex. Say, for example, you might be dealing with sequential data, time-stamped data, and you might have to analyze data that has been captured over several days or several months that is contiguously the sequence in which the data appears is important, and you might be ending up with analyzing data that has been collected over several days or several months, for example. Or you might be dealing with video data, sequential images. So you'll be dealing with image data or video data and so forth. So that we will be quite often dealing with such complex data as well. So these all aspects are involved within data mining. So we can broadly classify the aspects related with data mining as a predictive data mining as well as processing. So let us let us just discuss about what is this predictive data mining essentially looks like. So we will be highly correlating that with whatever machine learning techniques are. For the predictive data mining, so one of the prominent is classification. So about predicting some finite discrete outputs. Say, for example, whether a specific transaction that have a bank transaction that happened, whether it is a normal transaction or whether it is a fraudulent transaction. So we need specific techniques by which we can categorize a transaction as a normal or fraud. So that's what we here mean by finite discrete value. So in this example, we only have two different possible classification. The transaction can be either normal or it can be fraudulent transaction. So that's what we mean by saying finite discrete outputs. Another example here in these terms can be classifying your mail as a spam mail or a non-spam mail and so forth. That would be two other discrete possibilities. So that is one part of predictive data mining. The another one is about regression analysis, where the prediction is going to be a continuous value. Say, for example, looking at certain attributes, how we can predict the amount of sales for a company. So that is another aspect in regression analysis. And there is another important aspect called affinity analysis. So that commonly we call that as clustering as well. So the affinity analysis, what it tries to do is it is, in short, trying to group together similar elements. So that is essentially used in recommendation systems in business analytics. So say, for example, when we purchase some product from Amazon, for example, so we can immediately see other product recommendations showing up, like people who bought this particular product also bought certain other products. So it is highly likely that we will be interested in purchasing those products as well. So recommendation systems also plays a very crucial role in sort of business intelligence. We can also say that one of the prominent is this affinity analysis within business intelligence. And regression analysis, of course, plays an important role. And so this is all about the predictive data, the predictive analysis in business intelligence that we are talking about. So we base everything mostly, all the advanced business intelligence or the data science mostly bases upon data mining techniques. So pre-analysis data mining. So what it essentially means is that, so we already mentioned that data, a huge data, plays a crucial role here. So what are things that you can do with the data that you have? So there are some pre-analysis that you can use. Before we do these predictive analytics, there is some sort of pre-processing that we should do to the data. So say, for example, this text data can be available in the internet from many different resources. So how do we retrieve all those useful information from various different websites and then put them in a single format so that we can apply some predictive analysis on top of that? So we need to process the data. So collecting and processing, so there is a well-defined procedure called extract, transform, and load. So we usually abbreviate it as ETL. So that is a method of standardizing and centralizing the data. So one simple example you can think about is that, say, for example, we are selling some product through online portals. Say, for example, I'm selling a microwave oven, for example. I will be selling it in Amazon, for example. I will be selling it in Flipkart, or there could be various other online portals where I will be selling my microwave oven, for example. And what I'm specifically interested in is that I wanted to know what is the reviewer's opinion about the kind of microwave oven that I am producing and selling it through all these portals. So what I will be interested in is that I wanted to collect the review from all these websites, say, for example, from Amazon, from Flipkart, from Snapdeal, or whatever sort of online portals that you have, for example. You wanted to collect the reviews corresponding to that specific product, that specific microwave oven, and then I wanted to assimilate all the reviews and sort of process it and put it in a specific format so that I can apply some predictive analysis on top of that. Say, for example, I wanted to see whether on an average the customers is having a positive review about my product, or or customers are giving a negative review about the product. So we cannot actually go through, sit and manually read all these reviews. So there will be humongous amount of data. So we need to process the data into some structural format, and then we needed to apply some machine learning techniques on top of that to derive this particular analysis. So we generally call that as sentiment analysis, to see whether it is a positive review or a negative review, or are the people very neutral about this particular product and so forth. So that will help me to optimize my business. So that sort of sentiment analysis from deriving from the review of the customers will help me improve my business. So that is another important aspect of data pre-processing. So we're collecting from various resources and then putting it into a desired format to apply predictive analysis on top of that. Another important aspect is about data visualization. So that sort of gives an overview about the data that we are going to deal with. So specific techniques that we also looked in a previous session about visualization tools. In conjunction with this data visualization, there is one more additional advanced methodology, which we call as exploratory data analysis, which is usually referred to as EDA. So we apply, say, for example, several statistical and visualization techniques to derive some useful information, or get some vague answers answers to derive from. So from some large data sets, we can ask some questions. So how certain products or how certain events are related. So by doing an exploratory data analysis, we can sort of try to address such questions. A simple practical example that we can think in this context is that, say, in data analytics, we have this market basket problem that we usually take as an example in a data mining course. So in a supermarket, what products you should keep nearby so that it will help improve their business. So that is a very important. So that can be answered through these exploratory data analysis. So what all products are highly correlated that maximizes the business or the sales. So what products should be kept nearby? So whether near to the breads, should we keep eggs or butter and so forth. So rather than keeping bread at one place and keeping the milk or eggs or butter at certain other farther place within a supermarket, that might not be an optimal way of placing it. So we can, based on the product sales or the customer's buying behavior, we can ask certain vague questions like, what products should I keep nearby, so that will help the customers. Eventually, that will also help the business as well. So those sort of things can be understood through these exploratory data analysis. It's a very interesting aspect. So that predominantly also uses the data visualization technique. Also, as a side note, so whatever that Pandas data analytics tool that we looked in the third session, so that is predominantly used for exploratory data analysis, and we can answer many such vague questions from raw data that we take, and we should be able to address these as well. And another important pre-analysis is with data reduction. So that is essentially the dimensionality reduction concept that we usually discuss in statistical analysis. So we might be dealing with several attributes, and sometimes more number of features in a problem does not always necessarily mean it will lead to a better solution. Some features might be noisy. It might be actually affecting our predictive capability or a model's learning capability will be affected by features. So it is not always true that if you have more number of features, that is always going to help us solve the problem. So some features might be noisy, that might be affecting us. So there should be some strategy by which you can sort of try to discard certain features that are not very useful or that doesn't give us useful information and so forth. So to reduce the complexity of your data set, you can apply dimensionality reduction, say for example, projection technique. One of the prominent technique is called principal component analysis, based on which you can perform this data reduction. So this is a systematic way of reducing the dimension. So within data reduction, there is another concept called feature selection. Say for example, you are having 10 features in a problem. And it is not always necessary that all the 10 features are giving you discriminant information. Couple of features might be giving you same sort of information, which is not very helpful. So there is a concept called correlation analysis, by which you would see if two particular features are highly correlated, then it doesn't make sense to use both the features. Rather, you can decide to kick out one of the features and use only one feature instead of using two features which are highly correlated. That is not going to help us with say for example, learning better models. Rather, it is only going to increase the complexity because you are going to deal with more number of dimensions. So that is a concept called feature selection. So one thing to understand is that feature reduction is different from feature selection. So in feature selection, you are just kicking out some features which you feel like it is not very much discriminant enough or useful enough, where you retain the name of all the features as such. But in feature reduction, say for example, when you apply dimensionality reduction, the concept is slightly different from feature selection. So there, your original features attributes are being changed when you apply principal component analysis. So that's why when you apply principal component analysis, you no longer call that with the original feature names, but instead you will call it like PCA feature 1, PCA feature 2, and so forth. So you might have seen that in many research papers or in some projects that it is mentioned as PCA feature 1, PCA feature 2, and so forth. Why don't they call it with the original name? Because that property is destroyed when you apply PCA reduction. So that is something to keep in mind as well. Correlation is, you can say it is feature selection, but projection is feature reduction. So you should understand at least that intricate difference there. So now coming to business intelligence using the data mining. So the prominent technique used is the machine learning. So even though we say it like data mining is sort of an intersection between machine learning, statistics, and database systems, the prominent there is, or the heart is the machine learning for the business intelligence. So we might also even ask, what is the difference between statistics and machine learning? Many of the machine learning techniques also use statistical techniques. But when you purely look at in terms of the mathematical framework for statistics and machine learning, the statistics usually do not handle with very huge data. It does not involve optimizations, or it does not involve any computational techniques and so forth. But when you consider machine learning, it takes statistics and then applies on top of that big data analytics, does some computational mathematical optimizations, computational algorithms are involved, and so forth. So that is an intricate difference between statistics and machine learning. So machine learning, so even though we say it like business intelligence, it is essentially artificial intelligence domain, artificial intelligence applied for business decision making. So that's what this business intelligence is all about. But to the core, it is artificial intelligence. So artificial intelligence is something we can say like it is a application that helps to automate some tasks. So we can use business intelligence to automate some useful information retrieval techniques and so forth. So that is part of the business intelligence. So one of the prominent tools by which we achieve artificial intelligence is, so one of the prominent tool by which we achieve artificial intelligence is using the machine learning technique. So machine learning is a set of a collection of tools that can be used to build artificial intelligence. So why I have not sort of included machine learning as a subset of artificial intelligence is that it is not necessary that all machine learning tools should be necessarily used to achieve artificial intelligence. You can also use machine learning techniques just to derive some useful information to make some decisions, some subjective decisions as well. So in some resources, in some textbooks, you would see machine learning is said completely a subset of artificial intelligence. So that need to be understood in a very different context. So here I am explaining it in an additional concept that not all machine learning tools need to be used only for artificial intelligence, but it can also be used to do some subjective decisions as well. And machine learning is very prominently also called as statistical learning. So that used to be the most prominent synonym. You can say machine learning is also equivalently called as statistical learning. So whenever we talk about statistics, data plays an important role, because if you don't have data, you cannot apply a statistics on the data. So even if you wanted to do some minimal descriptive statistics like obtaining an average or finding a standard deviation, or what is the minimum or maximum or median mode and so forth, to do all these minimal descriptive statistics, you need data. Without data, you cannot obtain these things. So that's where data plays an important role in machine learning or statistical learning. And currently, the most prominent or the type of machine learning that is very prominent and getting a lot of research attention is called deep learning. So what I wanted to highlight is that these machine learning tools essentially makes use of data. Before these machine learning or statistical techniques were popular, artificial intelligence or these sort of business analytics was applied. That concept is called expert systems, or predominantly the most prominent concept called as symbolic AI. So that was a sort of a rule-based system based on which we were able to make these sort of artificial intelligence. But now the most prominent is the machine learning domain, and within that, one of the domain tool, we can say deep learning is a tool, one of the tool in machine learning which has gained a lot of popularity in recent years in the machine learning domain. So deep learning is nothing but a modern name for an old concept called artificial neural network. So this is just a new manifestation name for an old concept called artificial neural network, and it's a very interesting, and there is a lot of research opportunities in the domain of deep learning as well. So now machine learning being the heart of this business intelligence or even the data mining. So let us try to understand what these machine. I will just briefly sum it up, because I know that all through these data science sessions that you might have encountered all these concepts previously. So this will be sort of a summarization of all those concepts as a brief. And then what we will do is how we will implement one machine learning technique by which we can sort of see how business intelligence can be applied using a machine learning technique called regression analysis. But before getting into that, let us just try to get a brief overview or sort of a summarization of what we learned in all the previous sessions in this specific workshop. So trying to capture what machine learning is all about. So we have input and output mode for machine learning. So for any machine learning applications, there is an input and we are getting an output. But then how it is different from a conventional programming or algorithmic techniques that we are already familiar with. There also, for a program, we give an input and we expect an output, and we write a well-defined procedure, which we call it as an algorithm, to achieve a specific task. But machine learning is slightly different there. So it also takes input and output. But what is different there is that instead of we writing some algorithms, what machine learning is trying to do is going to apply some transformations to your input to get your output. So what it essentially is trying to do is that it is going to transform your input to the desired output. And now we can ask the question, what is this transformation? So how these transformations are estimated? So these transformations are estimated from the data that we are talking about. So this is the heart. So we should always remember, keep this particular block diagram in our mind, that this is the heart of machine learning. These transformations that is applied on your input to get the output. So these transformations are learned from the data. One example could be like, say we have, let us say we have 100 participants in this particular event. And our task problem is that we wanted to predict the height of the participant by looking at their weight attribute, weight, age, and gender. So that is a machine learning problem. So can we predict the height of a person just by taking note of the weight, age, and gender? So how that could be done? So we will collect these information from the participants, and then that becomes the data. So collecting the weight, age, gender, and height information from all the 100 participants, so that becomes our data. And now we are going to learn these transformation parameters from that collection of data, which transforms weight, age, and gender information into height information. So that transformation, say for example, let us call that parameters like C0, C1, C2, C3, and so forth. So since I have 3 attributes here, I'm showing here 4 parameters, transformation parameters, C0, C1, C2. So I will use these values to transform my weight, age, and gender information into the height information. And how do we apply this transformation? So you can just call this. So the transformation is shown at below. So I cannot bring the mouse pointer below, then immediately that pop-up message comes up. So let us just look at the bottom line. So C0 plus C1 times weight plus C2 times age, C3 times gender. So that is the transformation that we apply, and that information is transformed to height information. The height information that we predict is the continuous value. Say, for example, it can be 160 centimeters or 157.3 centimeters or 168.2 centimeters and so forth. So that is a continuous value output. So any transformations which gives continuous value outputs are called regression models, or we can call it like regression analysis. These C0, C1, C2, C3, which we call as transformation parameters, so they are in the machine learning context, we call that as model parameters. So C0, C1, C2, C3 are called model parameters. So once you know the appropriate values of these variables, we finally have a machine learning model. So these are called machine learning parameters. In classical machine learning, so one more thing, let me just highlight you. So here in this entire machine learning category, we have carved out. So this deep learning is one of the important tools. So now deep learning is so popular that machine learning is broadly classified into 2. So any machine learning tool other than deep learning tools are called classical machine learning techniques, and anything that is artificial neural network are called deep learning techniques. So we can broadly classify them into classical machine learning and deep learning. So now these transformation parameters in classical machine learning, these are referred to as theta 0, theta 1, theta 2, theta 3, and so forth. That's what the usual notation that we see. When we get into deep learning or artificial neural network, these C0, C1, C2 are represented as W0, W1, W2, etc. weights. So in classical machine learning, it will be mentioned as theta 0, theta 1, and so forth. In deep learning, it will be referred to as W0, W1, and so forth. But they both mean the same. So they all are these transformation parameters. They are going to transform our input to our required output. So that is something we need to keep in mind. No matter whether it is deep learning, it is just this transformation box. So inside that, you would have multiple layers of transformations. That is the only difference. You might have multiple layers of transformations or just one layer of transformation. So that's how classical machine learning and deep learning techniques differ, essentially. So if our output is a continuous value, we call that as a regression. If the output is going to be some discrete possible outputs, like classifying your mail as either spam or a non-spam. So in machine learning terminology, non-spam is usually referred to as ham, so spam or ham. So there are only two possible outputs for any input email. It can be either spam or non-spam. So if there are only such discrete or finite possible outputs, we call such problems as classification problems. So there also you are having transformations. These transformations can happen in multiple levels. You can have a first level transformation, and that transformation can be further augmented by another level of transformation and so forth. So here, one of the examples. So you might have encountered it previously. You might apply logistic or a sigmoid function on top of a regression. So you call that as a logistic regression or a softmax regression and so forth. So no matter what inside happens, so you can just term it as transformation. So your input is going to be transformed to a required output. So our entire machine learning approach is to find out what are these values, how to find out the best values for C0, C1, C2, C3, and so forth, so that our output is more accurate. Say for example here, these F1, F2, F3. So emails are essentially text data. So they are, say for example, paragraphs comprised of words. So these F1, F2, F3 from an email can be some unique words that helps us to distinguish a mail as a spam or a non-spam mail. So that's what we needed to essentially do. So we needed to, so once you get a text data like a paragraph or an email, we need to decompose that into some collection of words, which we call it as vocabulary. So that's a very interesting domain called natural language processing. So from using techniques in natural language processing, you will be able to decompose your mail into some specific number of input data. So now the question arises, like, how do we find these values? So C0, C1, C2, C3, and so forth, there are some values there. We can call these as variables, and these variables should have some values. So how to find that best value? So the heart of machine learning is the technique called gradient descent. So you can apply a technique called gradient descent to find the best values from these data. You can find the best values for C0, C1, C2, etc. Using gradient descent technique. So that's what something I wanted to highlight. If it is a deep learning transformations that you needed to find, so there is an improvement to gradient descent, which is called backpropagation. So that you can apply to find these values. So essentially here also the transformations are like that. So you take C0, so that is a constant term, which we call it as bias or intercept in machine learning. So you have C0, then you have C1 times F1, C2 times F2, C3 times F3, and so forth. So you get first level of transformation, which we call it as Y. And then you can apply another level of transformation, for example, a logistic transformation, and you get your output. So now we can ask the question, see these F1, F2, F3 here in the case of emails, they are words. So how words can be multiplied with numbers? C0, C1, C2, these are variables which are numbers. They are real numbers. So we cannot multiply real numbers with words. So what we do is, in natural language processing, there are techniques by which you can map words to some unique numbers, some integers, for example. You can map words to integers, or you can map words to points in a higher dimensional space, which we call it as word embedding. So there are some concepts by which you can obtain numeric representation for these words. And that is when you convert those into numbers, and then you can perform these mathematical operations. One thing to always keep in mind is that machine learning models can only take numbers as input, and it throws out only numbers. And it is left to us, how do we interpret those numbers? So in case of email classification, the output will be either 0 or 1. So it is left to us whether 0 should be called as spam or 0 should be called as non-spam. So it is how we manipulate. So that's what essentially this pre-data analytics part that we discussed previously about that ETA, that centralizing the data set and so forth. That's all involved here. So even though I have just mentioned about these two concepts about regression and classification, mainly depends on whether your output is a continuous value or a discrete value output. Regression can also be quickly transformed into a classification problem. Say, for example, here we are going to predict the height of the participant. If we say, for example, apply some threshold on top of that, say, for example, if the height is more than 160 centimeters, we call them as tall. If they're between 100 and say 140 to 160, we call it as medium, or less than that, we call them as short, and so forth. Then once you apply some thresholding, you are now getting it into only 3 discrete or finite possible outputs. So just by applying thresholding to regression, you can transform regression into classification as well. So that is something to keep in mind. They are very closely related. But any kind of problems that you deal in machine learning can be categorized as just 4 categories. So it could be either a regression problem, or it could be a classification problem, or it could be a clustering problem where you are trying to group together data which shares some similar properties, some sort of similarities. There are some metrics by which you can estimate those similarities, or it could be a dimensionality reduction type of a concept. So these are the 4 different categories. So any machine learning problem that you pick up, it will be either one of these or it will be a combination of these. And you can very well apply dimensionality reduction to all these 3 categories as well. So it can be independently used for some analysis, say for example visualization, or to reduce the complexity of the problem. But this dimensionality reduction can become an integral part of these 3 concepts as well. And one more important thing to remember is that regression and classification, they are called supervised learning, because you already need to know what is the actual output. So from your data set, you should know what is the actual output as well, so that you can train your machine learning model in a supervised manner. So this is the place we are trying to minimize some objective functions, some error functions like mean square error or cross entropy and so forth. And clustering and dimensionality reduction, they are unsupervised learning, where the output is not necessary. Just by data, you can analyze some similarities and group them together, or you can straight away apply some feature selection or feature reduction and so forth. So that's essentially under dimensionality reduction. So when you try to interpret them geometrically, so what I always suggest is usually in my courses, I usually suggest this particular point of view, that you always interpret machine learning as a geometric problem. So consider that all your data that you are dealing with, irrespective of the domain, whether you are dealing with agriculture domain, whether you are dealing with medical domain, whether you are dealing with computer vision or natural language processing, doesn't matter what your domain is. Eventually, all your data can be interpreted as a point in higher dimensional space, depending on how many attributes you are dealing with. If you are dealing with 10 attributes, you can consider your data as point in a 10-dimensional space. It is difficult to actually visualize them, but at least you can sort of have an intuition. All these points are, all your data are points in a higher dimensional space. So that's where specifically the linear algebra plays an important role in machine learning, where you are trying to interpret your data as points in a higher dimensional space, and then you apply many linear algebra operations on that to solve the problem appropriately. So for example, when you are talking about regression, so it is all about some clouds of points in a higher dimensional space. Here I'm showing it in 2D, but you can extrapolate it to any number of dimensions. And when you're talking about regression, and if your data happens to be linear, so when you want to say a data is linear, so you can, when you say take this as x-axis and y-axis, as x increases, if y is also increasing proportionately, we call such data as linear data. So here you can see on an average, as x is increasing, y is also increasing. Or the other way also you can mention, when x is decreasing, y is also decreasing and so forth. So such data are called linear data. So in linear data, what you are trying to do is you are trying to fit a linear geometry to best represent these data. So here a straight line happens to be the linear geometry that best represents the data. If you say, for example, thinking these points as clouds of points in a higher dimensional space, then instead of trying to fit a straight line, you are trying to fit a hyperplane. So extension of straight line into higher dimensions is called hyperplane. So you're trying to sort of fit a hyperplane that best represents the data. So that's at least the intuition you should have. Sometimes your data can be non-linear as well. So in that case, you cannot fit a linear geometry. Then you might need to come up with a non-linear geometry. For example, you might need to find a curve that is best representing your data. That is about regression. So you're trying to find the best representative geometry for the clouds of points. In terms of classification, you might have two different clouds of points. Say, for example, this can be spam mails represented as clouds of points. This is non-spam mail represented as clouds of points. Your task is to find a geometry that best discriminates, or a decision boundary that best discriminates these two clouds of points. So again, this is a geometry problem. What you are trying to solve is trying to find out the equation of the straight line or a hyperplane that is best discriminating, or that acts as a good decision boundary between these two clouds of points. It can be linear or it can also be non-linear. So in that case, you might be coming up with some closed curve, say for example, ellipse or a circle or so forth, that can best discriminate two clouds of points. Another kind of problem that we deal is clustering. So where you have initially some collection of points, and based on some metric, you are trying to group together points that belongs to similar category. This can be especially useful in making recommendations, building recommendation systems for business analytics. Say for example, you can say these are people who are interested in purchasing textbooks. These are people who are interested in purchasing, for example, kitchen utensils. These are people who are interested in purchasing some, say for example, clothes through the Amazon, for example. So what machine learning algorithms do is that we only have collection of people or customers. So what the clustering techniques does is that it tries to group together people who are interested in purchasing textbooks. It groups together people who are interested in purchasing utensils. These are people who are interested in purchasing dress and so forth. So how clustering based recommendation systems work is that if someone buys a textbook that another person has already bought, the system will look at what other textbooks people from this group has bought, and it will give you a recommendation. So that these kind of concepts are helpful. So you can think clustering as a in a high dimension. You can think it's a cloud of points. You need to assign colors to each of the points and sort of group them together. So that's what clustering is. And sometimes reducing the dimensionality can be helpful. So here, for example, a three-dimensional data, a cloud of point in 3D has been projected to a cloud of point in a 2D. So that can sort of help in reducing the complexity of our problem. So this is, for example, this visualization is achieved by reducing it using principal component analysis. You can see how it preserves the structure of the original data as well. So to summarize, so I don't want to go through in detail here. So you can categorize your problems as regression, classification, clustering, and dimensionality reduction, and there are various important algo techniques by which you can kind of solve these regression, classification, clustering, and dimensionality reduction. Say, for example, support vector machines or ensemble-based techniques. It can be used for both regression as well as classification. You can see support vector and ensemble-based techniques to do both regression and classification. So you can also see they are very closely related. And remember, classification and clustering are supervised techniques. Clustering and dimensional reduction are non-supervised techniques. And you can call clustering as an unsupervised classification. So that's what clustering is all about as well. So that is just a summary. So let us just try to understand how a specific machine learning technique can be employed for business analytics generally. So we are now currently going to look at how business analytics can be, or business intelligence can be implemented using a machine learning technique. So let us take an example here. So I have a collection of points under X and collection of points under Y. And our task now is find a relationship between X and Y. So how we can obtain Y based on X. Can anyone say how X and Y are related? How can you say Y is equal to what in terms of X by looking at this particular pattern? Can anyone give an answer? Y is equal.
Adding same number.
Sorry?
Adding same number to the x.
Yeah, so what is how do we write that as an expression? Y is equal to what?
2x.
Y is equal to 2x, right? So y is equal to 2x. So that's what I wanted to know. So we are sort of, even though we have a data, so we have trying to represent these data as an equation. So we are trying to find a relationship between y and x. Say for example, this particular data, how do we write this? Y is equal to what in terms of x? How do we write that?
2x plus 1.
2x plus 1, good. So we can also write it like 1 plus 2x, so they are essentially same. What about this particular sample?
X square. Oh. X square.
X square, correct. So y is equal to x square. So what about this? When you have a collection of data like this, x and y, how do we write it? So now it is not that easy. So here what we did is that here we were able to quickly understand a pattern. So we were sort of applying an intuitive pattern recognition, and then we were able to come up with this expression, how y and x are related. But that is not always possible. In real life, whatever data that you obtain, it is not that obvious. It might not be that obvious to find a relationship between how y and x are related. So here in this example, it is related like 4 plus 3x plus, and there is also some random noise involved in it. So we can always expect some random noises in the data that we collect. So it is not always possible to just look at data and immediately come up with how y and x are related. So we need some well-defined procedure by which we find the relationship between y and x. And that procedure is called regression analysis. So you're trying to find the relationship between y and x. So here we are just dealing with just one particular x. You can also have multiple x, and you can also write an expression based on that. So now we can ask the question, so what is the use of representing, or even here, what is the use of trying to represent these data using an equation? So when we think that, we can sort of answer it like, say, from out of this 10 data, by looking at this 10 data, we have encapsulated or tried to find out what equation could have generated this data. So if we know that for any unknown x, for some future x, so from this table we don't know what will be y when x is 112. But if you know this equation, you can always predict what is going to be the y for some x which you have not already seen. So that is the essential idea of machine learning as well. So from the data, whatever data you have, you are going to build a model. And for some unknown data, using your model, you can always make a prediction what it is going to be. So that is the essence of machine learning in general. So one of the terminologies that you needed to capture is this expression. For this expression, what do you mean by independent and dependent variable? For this expression, y is equal to 3 plus 2x, we call this x as independent, y as dependent. In this second expression, x square minus 2x, even though we have two terms here, but the number of independent variable is 1. We only have x as independent and y as dependent. We take this expression, x is equal to 5x square plus 8y cube. We have two independent variables, x and y, and your dependent variable, you call it as z. So what we understand from here is that x is free to choose any value. So based on what x chooses, y depends on that. So that's why y we call it as dependent variable, and x and these xy as independent variable, depending on the context. So when you write it like an expression, so whatever variables appears on the right hand side, you can call it as independent. To the left hand, it is dependent. So finding the relationship between the dependent and independent variables. So that is essentially the regression. So that is the essence of regression. So in a regression analysis, so when you take these first two expressions, you only have one independent variable. But in this expression, you have two independent variables. In machine learning, we usually deal with a scenario where you only have one dependent variable, but you can have one or more independent variables. So these are something which you call it as attributes, and this is your output that you are expecting. Intuitively, you can think like that. So in a regression analysis, if you have only one independent variable, then you call such analysis as univariate regression analysis. And if you have more than one independent variable, you call that as multivariate regression analysis. So that's based on how many independent variables you have. Say, for example, in a previous session, we looked at an advertisement data set, advertising data. So there, what we were analyzing is like, how do we spend the amount of advertising on TV, newspaper, radio, and essentially try to understand what is the sales that we achieve by advertising in TV, newspaper, or radio, and so forth. We had 200 data samples there, so we even used that to derive some descriptive statistics and some data visualizations. So let us try to use that particular data set to do a business analytics problem as well. So our task is to find out these transformation parameters, or to essentially find out the transformations. So just by saying how much you spent on TV, how much you spent on newspaper, and how much you spent on radio. So if you spend certain amounts corresponding to TV, newspaper, and radio, what sales you can expect. So that's what you wanted to address. So that can be addressed using regression analysis, essentially. So whenever you have data sets, so let us say, for example, so here I'm going to just introduce about the machine learning practice. I hope you have already went through that previously. So this will be sort of a summary for you. So in our advertising data set, we had 200 data, for example. So let us assume this is our entire data set, 200 data. I'm just showing it as a 2D for our discussion purpose, but here it is a three-dimensional data because you have three attributes. So how many attributes you have, you can call it also as the dimension. So if you have three attributes, you can say you are dealing with the three-dimensional data. If you have 15 attributes in a problem, then you are dealing with 15-dimensional data. So that's the essential idea. We can also since the maximum dimension with which we can visualize is a three-dimensional data. I will also show you how to visualize these data as a three-dimension. In the hands-on part, I will explain you how we can visualize this. But let me just summarize the machine learning practice. So we say learn from the data. So when we wanted to learn from the data, there are some machine learning practices that we should follow. So whenever you get your data, so let us say this is your advertising data. So this is your entire data set. X, you can call it like this. X comprises of TV, newspaper, and radio. So you have three dimensions. So this X itself, you can intuitively think there are three things inside that. And Y is the sales along the Y axis. So we are sort of, let us arbitrarily assume the plot of the data looks like this. In reality, it is not like that. I am showing it for discussion purpose now. We will visualize how the actual data looks like in a short while. So the machine learning practice is once you have your data, you have to split the data into training and testing data. And the most commonly accepted practice is you take 80% of your data for training and use the remaining 20% for testing. So this is your original data. So you have to split the data into 80% training and 20% testing. So how do we split it? So actually the procedure followed is you are taking from this entire point, randomly take 20% of the points and you take that as your testing data and the remaining becomes your training data. And let us call your training data as X underscore train, Y underscore train, for example. And your testing data as X underscore test and Y underscore test. It is a usual scientific practice to see your attributes represented using capital X and the output is represented using small letter y. So that is a common practice that we see in machine learning. Not mandatory, but good to follow this particular practice. Just to say that X will contain multiple attributes, but Y is just a single value. So that's why it is small letter Y. This is to just represent like a multi-dimensional vector. So that's why it is capital X. So that's the motivation why it is caps and small. So now splitting is actually random. So you take 80% training and 20% testing. You can, it is not mandatory that 80-20 should be the split. You can also take it like 70% for training, 30% for testing. But usually it is within that range, 70 to 80% for training and correspondingly 20 to 20% for testing. It is never seen that 50% for training, 50% for testing. It is not a common practice. Or you don't even take 95% for training and use only 5% for testing. That is also not a common practice because that is not a robust evaluation. So you need at least 20% data for testing. But the convention is more number of data for training and less number of data for testing. So that's the idea. So when you combine these two, you are actually getting your original data. So this is your original data, and all these red dots are your 20% training, some 20% testing, and the remaining green dots are your 80% training. So that's something to keep in mind. And what you are trying to do is you are trying to find the best representing geometry. So we can ask the question whether this line is best representing these set of points. So when we just look at it, it seems like it is not the right way, right straight line that represents the training data. We can ask another question whether this straight line best represents the data. This is comparatively better. So comparing to this particular straight line, this straight line seems better. It is almost trying to represent the data, but we feel like there could be another straight line, a better straight line that could be best representing this data. If we ask whether this is okay, we still feel like that is not okay. So when we look at this particular blue line, we feel like, yes, so this seems like sort of best representing the data. So what we are doing is, using machine learning technique, what we are trying to do is, we are trying to find out this, out of all these possible straight lines, what is the best representing straight line. So that's the essential core idea behind even gradient descent technique. What gradient descent technique is trying to do is that it is trying to find out of various possible straight lines, which is the best representing straight line. So geometrically, we can visually look at it and say this is the best line, but when you wanted to program it, you need some strategy by which we can actually find out of all these straight lines, which is the best fitting straight line. These various possible straight lines in machine learning terminology, we call these as hypotheses. So this dashed purple line, this is one hypothesis. This is another hypothesis. So there are, you can say, in this example, there are 4 different hypotheses. And our task is to find the best representing hypothesis. And that is going to be this blue line. Hypothesis is nothing but the equation. So whatever variables that we should know, that C0, C1, C2, and so forth. So those transformation parameters are called hypotheses. So we need to find the best hypothesis, meaning we need to find the best model parameters. So once we find that, so we can use that to evaluate whether how good our hypothesis is. In representing the data, we can test it. So we can evaluate it using our test data. So that's why we do this. Even in a very advanced analysis, we even split the training data into training and validation. So generally you have training data, validation data, and test data, but we don't have time to discuss those advanced concepts. So let us, at least in the broader sense, there is this training and testing split, and you need to evaluate your data on your testing data set. So the validation is used for some internal evaluation purpose during training itself. Say here, since this happens to be a linear data, our hypothesis is to look for straight or linear geometry, straight lines. If it happens to be a non-linear data, then if you try to look for a linear hypothesis, try to fit the data using a straight line, it will not best represent it. So that means you will end up with a a concept called underfitting in machine learning concept. So what you have to do is you need to find a nonlinear geometry to best representing the data. Even when you are looking for the best representing geometry, you might also end up with something called overfitting in machine learning. So there are techniques by which you can handle that as well. So at least this is an introduction part that I wanted to summarize it. So we said like geometrically when we look at it, we know blue line is good. But how do we write some program? So that is captured based on the error. So if we draw a straight line between this point to this particular blue line, so there is a distance. Let us call this, there is a distance between this green point to this blue line. We call that as, we can call that distance as an error. The error of this blue line in capturing this green dot. That is what this distance means. So another distance here means the error of this blue line or this hypothesis in representing that point. If a green dot happens to be lying on top of this blue line or this hypothesis, then the distance will be 0. Then there is no error for this blue line or this hypothesis in representing that data. But for other points, there are some errors. So what you are trying to do is you are going to accumulate these distances, these errors. I have just shown it for 5 points, but you have to do it for all the 80% data that you have. So you will have 80 distances, or if we assume 80 points in this training data set, there will be 80 distances. You add up all those distances, you will have a total distance. For another hypothesis, do the same. So you also add up all those distances, there will be another total distance. So our criteria is find that hypothesis or find that geometry for which that total distance or the total error is minimum. So that is the best representing hypothesis. So that is how we programmatically try to solve this. And once you have the hypothesis which is having that minimum total error, we will use that to test. We will use that to evaluate it as well. So that is the core. So this particular error that we capture here. So say for example, this straight line that we are mentioning here. So to represent that straight line, we need, in mathematics, we write it, the equation of a straight line as y is equal to c plus mx. So c essentially controls the up and down movement of the geometry. The m, the slope, essentially controls the inclination of this geometry. So for some particular c and m, we are defining this blue line. So for various values of c and m, you have various straight lines in various height and various inclinations. So that's what we were looking at, various dashed lines and so forth. So there is some particular value of this y-intercept and slope, which is corresponding to this blue line. So our task is to find that. So if you extend it to higher dimensions, it will be equation of a hyperplane that we are looking for. In 2D, here you are looking for the equation of a straight line. So in machine learning context, we do not write it as y is equal to c plus mx, but rather we write it like w0 plus w1x, for example. Some places you will see it like theta 0 plus theta 1x, but it's all the same. So they are called model parameters. And this w0 is the intercept, the y-intercept part, which we said. And sometimes this is also referred to as bias. In deep learning, generally, this is called as bias. And these are called coefficients, the weight coefficient. So this is in the context of univariate. Say if you wanted to extend it to multivariate, this expression will look like this. If you are dealing with n attributes, you will have n coefficients, w1, say w1, w2, w3, and so forth. And to that, there is additionally a bias or an intercept as well. In many places, so this is geometrically, you can think this is the equation of a hyperplane. Previously, this is the equation of a straight line. Extended to multivariate regression, this is the equation of a hyperplane that you are looking for. And usually, you will see the output of your machine learning model is represented as y hat. So that is the usual term notations that is used in machine learning. You will also see that this expanded expression being compactly written as w transpose x as well. In many places, you will see this expression is written briefly as This is a vectorized representation, which is written as W transpose X. If you are dealing with theta 0, theta 1 representation, you will see that as theta transpose X. This term is written as theta transpose X. So in some places, you will also see about this being represented as the hypothesis. So this is what we are looking at. So HW of X, for the different values of W, we have different straight lines. So we can call them as different hypotheses and so forth. So that's the essential intuition that you needed to look at. In a detailed lecture, I also give it how we derive at these two equivalent representations, but we can't discuss that now. So the kind of error, so here let us just go here, this previous one. So here we are saying, like, out of all the possible hypotheses, for each hypothesis we are adding up the distances or the error. So we will have a total error. So we choose that hypothesis for which the total error is minimum. So how do we find those total error? This total error, so you can sum up all the value, you have a total error. If you divide it by the total number of points, you will get sort of an average error. So from the total error, you will get an average error when you divide it by the total number of points. In regression analysis, the most prominently used methodology to find those error is called mean square error. So that is called the error function, which we call it as mean square error. So this HW is, you can think, for different W, you are looking at different straight lines. So your task is find that straight line for which this mean squared error is minimum. So this is the expression. So this is called objective function or a cost function or error function. They all are same in different names. So your task is to find the value of W's. So this W means you should think it contains W0, W1, W2 up to Wn. So your task is to find that set of W0, W1 values for which this expression is minimum. In a mean square error, there you can straight away find that using normal equation, but you can also find these values using gradient descent approach. But there is a simple way by which you can find the best values, which is called normal equation. So if you use this expression, so this is derived actually by taking the first derivative of this equation and equating it to 0. But let us not get into those derivations. But that is called normal equation, which is called the closed form solution. So if you plug it in your training data into this expression, you will get the best values. So otherwise, to say, you need not look for all the different straight lines, but you can get the equation of the blue line straight away if you use normal equation. But that is not feasible in all scenarios. In some scenario, you cannot use normal equation, but you needed to adapt a technique called gradient descent to solve that. Here, this mean square error is the cost function for regression analysis. Say, for example, if you are dealing with classification problem, for example, then the cost function or the objective function which we use is called cross entropy, otherwise also called negative log likelihood. So for such an expression, for that equation, you don't have a closed form solution at all. Then in that case, you have to definitely use gradient descent technique to find the best theta parameters or the best model parameters, thetas or w's, depending on the context that we use. So now, once we have, so here I have shown like once we have these model being estimated, we needed to evaluate it. So when you wanted to evaluate it, we need some numeric to say how good our model is. So from these testing, 20% testing data, we will use those testing data to come up with a final value saying, okay, this is good, this much percentage good, and so forth. So for regression analysis, the most prominent evaluation technique is called R-square, which is also otherwise called as coefficient of determination or goodness of fit. This is a ANOVA technique. ANOVA stands for analysis of variance. It is one of the statistical method. So based on that R-square value, we can say how good our machine learning model is. So this is the expression for R-square, 1 minus SS residual by SS total. So let me tell you what is the intuition. How do we intuitively understand this equation? So this SS residual is the error of our machine learning model. this SS total, so whatever that is coming in the denominator, so this SS total is the error of an average model. So what this average model means is that, say for example, predicting the height of the participants by looking at the weight, age and gender, for example. So what we have is we have 80% training data. So what we will do is we will take the average height of the 80% participant in the training data. And no matter what the weight, age or gender is, we will always tell the average height from the training data as the height of the participant from the 20% testing data as well. So that error is called SS total. That is the simplest solution. That is the simplest model that we can come up with. So what R square is capturing is how good our machine learning model is with respect to the simplest model. So that's what this R square is capturing. If our model is value is close to 1, that means our model is doing a good job. If it is close to 0, it is not doing a good job. So now let us just quickly, so I have essentially introduced the concept. The hands-on is not that complicated, it is very easy. So I will just explain how we can actually.
Hello, Dr. Prasad, excuse me.
Hello? Yes?
Yes, sir. So we have reserved last 15 minutes for questions and answers. May I request you to please conclude the session?
Yes. So we can conclude in 5 minutes. So we can just come. I will just show that, and then we will have at least 10 minutes for the discussion part.
Okay, thank you.
Yes, sure. So now let us see how we can use that advertising data set to make those predictions. So our question is, if I spend certain amount in TV, certain amount in newspaper, a certain amount of money for radio advertisements, what kind of sales I can expect? So that's what I wanted to show. So I have provided this IPython notebook for regression sales prediction in today's download. So you can upload it into Google Colab and you can look at those results, but I will just tell you those important results. So let me just connect it. So let me just zoom in here. So this advertising data set is taken from this particular link. So let me just show you. This is an excellent textbook for machine learning, an introduction to statistical learning. Though the applications are written in a statistical package called R, but you can always interpret that in Python as well. But all the concepts for machine learning are extremely well written in this particular textbook, an introduction to statistical learning. I have understood many intuitive concepts being well explained. So I have understood many intuitive concepts by reading this textbook. So I highly recommend you to also go through this particular textbook for classical machine learning. So this is the advertising CSV, which that is also used in the regression analysis chapter in this book. So I'm just showing you that. So so let us just download that data set. So you will already have that on your left-hand side. So this is the advertising.csv file that we are going to look at. So let us import all the necessary library, and we are reading the advertisement CSV using pandas read CSV file, and we can look at the head part. So this we have already went through in the previous session. So what our task is, our attributes, looking at TV, radio and newspaper, we needed to predict the sales. So X should be TV, radio and newspaper. So from that data frame, we are taking out TV, radio and newspaper, call it X. So our X will be TV, radio and newspaper. And what we needed to predict, our output is sales. So let us put that under small letter y. So let us call that as sales. So now you have your data, X and Y. X is your 3-dimensional data, which is your input. So you'll have 3 columns. That means you have 3-dimensional data. So you're dealing with 3 attributes. So that is your X, and this is your output. So using the Matplotlib's toolkit, we can actually look at 3-dimensional visualization. So I'm just taking TV, radio, and newspaper, and then just visualizing. Let us visualize that data here. So you can go through the internal details later. So this is our data set, our entire data set. So this is our, so what we needed to do is we needed to split this data into 80% training and 20% testing. Using the 80% data, we will train our model. Using the 20% testing data, we will evaluate it. So we are using a machine learning library called scikit-learn. So that is the most prominent library for classical or statistical machine learning techniques. So from the scikit-learn, there is a function called train test split, which is defined inside the model underscore selection. So you can use that function. You pass your x and y, mention how much of the data should be testing. So here I am saying 20% of the data should be testing. So that's what I specify 0.2. And here is a variable called random status 42. That means every time you run the experiment, you have the same splitting. So that is called seeding a random function. So that's essentially what we are doing here. So this function will throw out 4 array. So you catch it appropriately using x train, x test, y train, and y test, these 4 variables. So x is splitted into 80% training, 20% testing. Y is splitted into 80% training, 20% testing. So let us just go ahead and execute it. So now you have your 80% data. So I'm just printing the shape. So out of 200 samples, 80% is 160. So 160 samples goes as your training, and your 20% of 200, which is 40, goes as your testing data. So let us just visualize that splitting. So all the green dots I am showing here, that is your training data, your 80% training data, 160 samples. And all the red dots here are your testing data that on which you are going to evaluate it. So now, how to solve that, how to come up with that regression model. So in scikit-learn, there is a module called linear regression. So using this regression analysis, we are going to solve that. So create a linear regression model. So you are essentially generating an object to this class linear regression. So this is a class linear regression. Generate a model, call a function called fit. So this is actually trying to find out the best model parameters using your training data, x train and y train. Once you have generated the model, you can evaluate the model using the score function. You pass your 20% testing data, x test and y test, you get your R square value. So this R square is the one which we already saw previously, the ANOVA technique, 1 minus SS residual by SS total. So that is the value you will get. So let me just print that. So you are getting that your model is 90% good. You can say, like, for predicting the sales, you are having a linear regression model that sort of 90% accurate. So how do we predict the model? So this is your testing data. Say this is your 40 samples, your testing data. So let me just show you how the prediction is. Let us take the first sample. So the first sample in your test data. So if you spend 163.3 units or that much amount in advertising in TV, and 31.6 in advertising in radio, and 52.9 in advertising in newspaper, we can see how much sales you can expect. So our machine learning model is predicting that. So let us look at that. So the predicting is 16.4 is the sales that you can expect. That is what our model is predicting. Let us look at what is the actual value of that prediction, that sales. So that is contained in y underscore test. So when you print that, you can see the actual value of sales is 16.9. Our model is able to predict very close to that. Our model is predicting 16.4. So this is, so you can see we have come up with a machine learning model. Given certain amounts for spending in TV, radio, and newspaper, our model will tell you how much sales you can expect. So this is a brief hands-on for how we can come up with a business analytic implementation using a machine learning. So that's a brief hands-on for a regression analysis. So now we can open it for question and answer session. Yes.
Yes, thank you, Dr. Ram. So there are a lot of questions. First one is, what is gradient descent?
See, that is a technique by which we find the best values of those transformation parameters. So we are having C0, C1, C2, and so forth, we were saying, right? To transform your input to output. So they are called machine learning parameters. So how to find the best value for those parameters? So we have a well-defined technique called gradient descent. So that is actually used to find the best parameters. So it is a technique to find the best model parameters. That is called gradient descent. Is that?
What is the difference between gradient descent and SVM?
And what?
SVM, support vector machine.
Support vector machine is a machine learning approach. Even within support vector machines, it uses gradient descent technique to find the best parameters. So support vector machine is a max margin classifier. It is essentially defining a decision boundary. It will either give you a straight line or a curve. So how to find the parameters of that straight line, which support vector machine finds? Those straight lines parameters are estimated using gradient descent. So gradient descent is internally used in support vector machine. So you can say like 99% or 98% of machine learning models use gradient descent. Techniques like decision trees or random forest or decision trees and random forest does not use gradient descent, but other techniques, even deep learning, uses gradient descent to find the best model parameters.
Sir, next question is, what is the difference between multilinear and multivariate?
Sorry,
Multilinear and multivariate.
So the multivariate is the scenario where you have more than one independent variables or attributes. Here we can say TV, radio, and newspaper. You have 3 attributes. So this is called multivariate scenario in machine learning model. And if you are trying to, if these data happens to be linear, and if you are trying to fit a linear geometry for the multivariate scenario, then we can call that as a multilinear analysis. If you happen to be, if your multivariate data happen to be non-linear, then you will have to go with non-linear aspect. So that is how it differs.
Sir, this is question from my side. What is the difference
Yes.
between multiple multilinear regression? There is one thing, and another thing is multiple regression. So are they different or the same?
See, for example, when I was showing about expressions, when we were looking at expressions here. So in this example, we are always, or predominantly, we deal with regressions which contains only one output. But there could be scenarios where you can have more than one output, more than one dependent variables as well. So we can even have some advanced analytics. So that are called multi-regression. Is that clear?
Yeah. Okay.
If your output is just one value, it depends on whether your output is just one value or your output is multiple outputs.
It basically, how many outputs do you have? We differentiate between these two.
Correct. Yes. Any other questions? I can't. Maybe I can try to read. Is there anything post here?
Yeah.
I can stop the presentation here. Okay.
So it starts after this is 1309. The question starts with, that time. By May.
Zero. Difference between, so that is already mentioned.
Second part of the same.
So what is the synonym of independent and dependent variables in machine learning? So the independent variables that we mentioned here, they are called as features or attributes. They are called features or attributes usually, or we can also call them as dimensions. And the dependent variable that you have here, they can be called as labels or targets. So that's what usually the terminology used in machine learning. So the labels or target is the dependent variable, and attributes, dimensions, features, they all are synonyms for the independent variables. Hope that is clear. Any other questions?
Yes, sir. Next question here, I can see. What is validation data? Can you explain CHAD and KNN? CHAID, I don't.
So I can just mention you about validation data. We can't discuss the remaining part. So the validation data is used, for example, when training your machine learning model, you wanted to see how good your machine learning model is performing. So that using the validation data, you can sort of get an idea how your machine learning model will perform on the data it has not seen. So when we are training, we have two kinds of evaluation: training error and validation error. So training error are those which the model has already seen, and it is trying to see how good your model is predicting the data which it has already seen. Validation error captures how good your model will predict on data which it has not seen. So when you try to interpret these training error and the validation error, you can try to analyze whether you are dealing with a high bias, high variance scenario or not. So there is something called bias and variance trade-off in machine learning that essentially says whether you are dealing with underfitting or overfitting your machine learning model. So this validation data essentially helps us to gain that intuition and think about how those underfitting or overfitting scenario can be handled. Say, for example, there could be techniques like regularizations that you can use to handle it, resolve it. Or sometimes it could be like you need, no matter how much regularization you apply, you are not able to resolve it because your data is not good enough or enough to train the model and so forth. So to do all those sort of intermediate analysis during the machine learning experiments, we use the validation data. And there is also a concept called cross-validation in machine learning, which essentially tells you how robust your machine learning model is when you slightly change your training data sets. So among slightly different training data sets, your machine learning model will the performance will slightly vary. So you are trying to capture a robustness of your machine learning model. So if it is trained on a slightly different data set, how the performance is going to fluctuate and so forth. So these are various aspects related with the validation data set.
So the next question is that I would like to know how is it possible to visualize the data that has more than 3 dimensions?
Correct. So you can either use principal component analysis. So you can visit the scikit-learn's documentation, look at how principal component analysis is used to reduce, no matter whether you are having 100-dimensional data, you can reduce that into 3 dimensions or 2 dimensions. So once you reduce that into 2 or 3 dimensions, you can always visualize it. So that is one way, PCA. And you can also look at a technique called TSNE, which is one of the most popular for visualization. So you can look for that T distributed stochastic neighborhood embedding. So you can look at these 2 techniques to visualize your data. So that will sort of give you a holistic view of your entire data set. Hope that is clear. Yeah.
Mr. Mang want to implement a stock market prediction and portfolios optimization using Python. So he is asking, can you suggest me some resources for the same?
Not clear. So which timestamp could you tell me? I can read it.
19, 1319.
Okay. How to implement a stock market prediction and portfolio optimizations in Python. Any resources? See, the stock market prediction. These all are related with time series data. So the regression analysis which we saw now, Even the stock market prediction is also a regression analysis problem. That is for sure. But we cannot straight away apply this linear regression technique to that particular time series data. So there are certain techniques by which you have to adapt to deal with time series data. And one of the most popular architecture that is used to handle time series data is called recurrent neural network. Even though it is part of deep learning, but a recurrent neural network is a very popular technique which has been used for several years to analyze time series data. So please search for solutions about time series data, how we can process the data to adapt it for a particular architecture. So that should be helpful. But I don't know exactly resources to mention as of now. But essentially, you should look for time series data prediction. You can look for scikit-learn. In scikit-learn, you can look for how to handle with time series data. We can use tutorials from TensorFlow or PyTorch. These are two prominent libraries that contains recurrent neural network implementations. So within recurrent neural network, the two popular architectures are called LSTM and GRU. So you should essentially look at LSTM and GRU examples to apply it for time series data, essentially. I hope that answers. Any other?
Yeah, I mean, this is it, but many participants, they are interested in some study material on Python or some references for the same Python deep learning. You have suggested one, introduction to statistical learning. So I mean,
Yes, yes.
because some of them are from different backgrounds, they want to know from where to start with. So this is a kind of generalized question everybody is asking.
General question. So one place that I highly recommend is the Kaggle. So Kaggle is an online data science portal. So Kaggle has a set of courses. So that is an extremely good for beginners. So Kaggle has courses for Python introduction, the Python visualization tools, and it has introduction to machine learning. It has introduction to deep learning. So I highly recommend beginners to start with the Kaggle's course. You can search in Google Kaggle's course for Python, for deep learning, and so forth. So there is a collection of courses that you can cover it in 1 or 2 days. Each course you can cover it in 1 or 2 days. So that is a very good starting point. And then coming to textbooks, so one textbook I recommended for classical machine learning is the Introduction to Statistical Learning. And if you wanted to, say, for example, deep learning, when you wanted to come into deep learning, it is slightly awkward that there are no very good textbooks because it is one thing is it is a very fast progressing domain. So no textbook can be sort of capturing all the concepts. So any textbooks that you eventually look at, it becomes quickly outdated. But there is a very standard textbook called Deep Learning textbook written by Ian Goodfellow. So I'll just type it here, the author name. So Ian Goodfellow. So that is one textbook. And another, you can search for Michael Nielsen. So these are two different authors. So please search for this Ian Goodfellow with the term deep learning, and search for Michael Nielsen's with deep learning. So that should give you a very good material for deep learning fundamentals. And if you wanted to, so they don't explain about the hands-on or the practical sections. So if you wanted to get into practicals, you look at the tutorial sessions of TensorFlow. So TensorFlow is one of the prominent deep learning library from Google. You can also look at PyTorch. PyTorch is a deep learning library maintained by Facebook Research. So these two libraries are very popular in both academic and industry. So please look at their tutorial sessions so that they teach you how to implement stuff. And for classical machine learning, you can look at the scikit-learn's tutorial. So that should also be helpful for you. I hope that answers.
Yeah, so there are no more questions, but again, a very general concern that because the participants have attended many lectures on data science, including yours, but I think that some of them are too technical and they do not know how much maths and behind the scenes things they should know, and or they should start implementing using the libraries. So can you elaborate on that a little bit?
How much of maths is required? You're asking that, is it?
How technique they should know their everything about the techniques, or they should start using the libraries and implementing them. It is a trade-off again.
Yeah, so yeah, that is correct. That is the right thing to discuss. See, when you straight away hit at the TensorFlow or uh, PyTorch tutorials, you might be able to download that code and run it in Google Colab, for example. But if you wanted to make any modification to that, then it becomes impossible, because only if you understand the fundamentals of the concepts, then you know what these specific code segments actually implementing, what it means, and that is where you can actually apply the modifications. But then to understand those concepts, you need to read these at least these Ian Goodfellow or Michael Nielsen's textbook. So when you hit there sometimes in academics they always say like you have to learn certain linear algebra, you have to cover some probability and so forth. So that is a trade-off. You need to at least understand just very minimal linear algebra and probability concepts, and maybe you can start looking at some online courses. So I exactly haven't gone through any of the online courses, but many people say that there are courses in Coursera online portal which is helpful. So maybe you have to follow that, and then whatever mathematics at that point of time you needed to understand, you backtrack and try to understand it. So that is the best way. So if you feel like let us cover all the mathematics and then get into machine learning, that is sort of very difficult. So the best is maybe you start with some course or pick a textbook, start reading it, and whatever mathematical concepts that you wanted to understand, you just backtrack and read. So you might need to understand some linear algebra concepts, something related with differential calculus is required. So these are some essential things that is needed. But it is all a long-term process. It takes a lot of time to cover up all those. But if someone teaches you with these balances, so in all my courses, I try to maintain a balance between the theory, and I introduce all the mathematical concepts that is required, and then I also parallelly explain the hands-on. So when I used to conduct 3 to 5 day continuous courses. So many people who have attended that, they have said like that was very useful, that there is a balance. So they are able to understand whatever mathematics is required. So that happens only when we conduct it as a course and we just explain what concepts is required. So when I explain about gradient descent, that is where I explain what is differentiation, first order derivative. What do you mean by a gradient? What do you mean by Jacobian? What do you mean by Hessian, and so forth? So that will be helpful. So it depends. So it depends on with whom you learn it. If you wanted to study it by yourself, it is a time-consuming process. That will take a long journey. So that is there.
Okay, thank you very much, Dr.
Yes.
Gave your time.
And if there are some research scholars, then definitely some level of mathematics are required. And even upon request, I am also starting an online course on advanced machine learning practices that will be many useful for researchers especially. So many people have already shown interest, so I will be starting it in January. So if you are interested, you can also join that course. So that is only a 3-month course. So if that will cover a balance between both theory as well as practice, and it will also involve implementing research papers, reading and understanding research papers, implementing them and trying to apply some modifications. That all requires some sort of expertise. So at least that is required when you enter into machine learning domain, if you wanted to do some research works and so forth.
In fact, participants are asking about the online courses by you. So I think it's going to be started in January, right?
Yeah, it will be in January. So you may mail me. You can mail me, and I will tell you the details about that. ram.krish@visioncorp.com. So you can mail me that. So even in this website, in the slides also, in the very first slide, I have given my email as well as my WhatsApp number. So you can call me as well. So if you send me WhatsApp, then I will also share. So the course contents and all those schedules will be sort of consolidated only by mid of November. but then the course will start in January. So I will tell you those details if you contact me.
Okay, thank
Sure.
you, Dr. Ram, for sharing your knowledge, sharing your valuable time, and you also accepted our request even after rescheduling your session, and it
Sure.
so very very thank you for the same. Thank you much, and we will hopefully hope that you will again join us in the online webinars and yeah, I think there is
Sir,
more question.
yes, sir.
Yes.
uh, Mr. Mayank, he's asking, sir, why only BTech CS are considered for ML or AI or DS jobs? Can a commerce guy be trusted for this job?
See, if one understands the concepts behind machine learning, and if one knows how to use the machine learning tools, then of course they can be relied. Because when you come to machine learning, you need not have too much of programming expertise. You are not going to build a very robust software. You already have the libraries, say scikit-learn, TensorFlow, or PyTorch. You only need the expertise how to call the specific API function calls and achieve the task. So that is okay. So even a commerce person, that person with a commerce background, can definitely do a good job in machine learning. So it depends on, so if the person or the candidate understand the concepts well, then that is fine. It's perfectly fine. But I don't know why only BTech people are being preferred, because maybe they have more programming expertises and they might be useful if a company hires a person in case, for example, after a couple of months that project which they were working on didn't continue, for example. Then if it is a BTech student with some programming or computer science or electronics and communication background, they can quickly deploy, change that person and put it in another team. But that might not be the case with the guy who has only commerce background and with only ML knowledge. Then the scope of that candidate to be put in other projects is a bit limited. So from a company point of view, they might think twice before recruiting. So that is the practical aspect. I hope that answers it.
Okay, thank you, sir.
Yes, yes.
Uh, we are we all are here grateful to you. Thank you
Thank you,
for
sir.
thank you very much for sharing your valuable knowledge and your time with us, and your cooperation, especially even after rescheduling of the event. You are ready to deliver the talk. Thank you, sir. And
Thank you very much.
in future we'll have more sessions with you,
Sure,
because we
sure.
are
So
going
if you,
to organize one more
yeah,
event, and in that event I hope you will be there for us. Thank you, sir.
sure. So then we can run a short course so that it will be useful for many researchers as well.
Yeah,
Sure, sir.
definitely.
Okay,
Thank
And
you,
sir.
sir.
Okay,
all
thank you very much, and thank you very much to all the participants, and I wish you all the best. Thank you very much, and thank you very much for your kind words. Thank you.
all the participants are now requested to join the next session at 2:30 p.m.